Moments of inertia, type 4, rolling discs and pulleys, A, inclined plane. So in 2000, question 8b, we had a uniform disc of mass m and radius r rolling from rest without sliding and 30 meters down a plane of angle 30 degrees to the horizontal. So we've defined, first of all, the linear speed of the disc after rolling 30 meters down the plane. So the first thing we want to do is draw a diagram so we can see what's going on here. Okay, so if we look at our disc on our inclined plane, the plane is an angle of 30 degrees. And because it's not sliding, it's going to have angular velocity. In other words, it's going to rotate down while also having linear velocity. So it's going to be moving in a linear direction, but also rolling at the same time. And we want to know, as it goes down a distance of 30 meters, what's the linear speed? Okay, so of course we need to know what's its change in height. And if I look at that, if I basically complete that right angle triangle there for the height, well then we're going to have opposite over hypotenuse. In other words, we have sine theta equals our opposite over our hypotenuse. Can't say that today. Okay, and then if I sub in my values, what we have is sine 30 is equal to the height, or the change in height over the hypotenuse, which is 30, and therefore h is equal to 30 sine 30 degrees. So in other words, the change in height will be 15 meters. Okay, and we know it's a disc. So because it's a disc, we're going to have our moment of inertia. And the moment of inertia of our disc is a half m/r squared. And of course, if you can't remember that, our moments of inertia is page 53 in our maths tables. So our mass is m and our radius is r. So our moment of inertia actually is just going to be a half m/r squared. We don't have to make any amendments to that. So now we have our change in height and we have our moment of inertia, so we're ready to start our question to look for our linear velocity. So because we have the disc rolling down the hill, as I said, there's going to be angular velocity and therefore linear speed as well. So therefore it's going to have kinetic energy broken down into two parts. So kinetic energy with our linear speed and kinetic energy with our angular speed. But of course our principle of conservation of energy is going to apply here. So in other words, the loss in height, in other words, the loss in potential energy will equal our gain in kinetic energy. So we're going to have our change in potential energy will equal our gain in kinetic energy. So a half mv squared for the linear speed and a half I omega squared then for our kinetic. And of course, both those kinetic energies can be found on page 54 and 55 of your maths tables. Okay, so what's the mass? Well, the mass is just m times g, and we saw the change in height was going to be 15. We have a half times m. Our linear speed is what we're trying to find, so I don't know what v is. And then we have a half times the moment of inertia, which is a half m/r squared, times the angular speed. And again, we don't know what the angular velocity is either. So of course, we don't want two unknowns here. So what we have to look at is the relationship between our linear and our angular velocity, which is v is equal to omega r, which is page 51. Okay, so let's tidy that up then. So that's 15 mg is equal to a half mv squared plus a quarter m or squared. And instead of omega squared, we're now going to have v over or to be squared, which is v squared over or squared. You can see I can divide across by m there. And of course, or squared is going to go into or squared once. That leaves us with 15g is equal to a half v squared plus a quarter v squared. And therefore that gives us then v squared is equal to, so that equals 20g, and then v is equal to the square root of 20g, which is of course 15 meters per second. Okay. So we have our linear speed of the disk after rolling 30 meters down the plane. So the next thing that we want to find here is the time taken for the disk to roll 30 meters down the plane. And again, we have to be careful here because if we want it corrected 2 decimal places. Okay, so we have the, I'm sorry, that shouldn't be 15, that should be 14, my mistake, sorry. Okay, sorry, so we want to find now the time taken. So what do we know? Well, we know it starts from rest. So that means the initial velocity is 0. The velocity when it has travelled 30 meters is 14 meters per second. And we know that's travelled 30 meters. So that'll allow us to work out what its acceleration is going to be. So we'll have v squared is equal to u squared plus 2as. Or the fact that we have s, u and v, we could also use s is equal to u plus v over 2 times t. So that's up to yourself, whichever you see first. I know I need a for the next part of the question, so that's why I'm actually going with v squared equals u squared plus 2as. So if I sub in, v is 14, u is 0, 2 times a times s is 30. And then I'll have a, if I get that on its own by rearranging everything there, I end up with a is equal to 3.27 meters per second squared. So of course, if you've used s is equal to u plus v over 2 times t, you'll have straight away gotten t in one go. So if I now have my acceleration, all I need to get is my t, so I can use v is equal to u plus at. And my v is 14, u is 0, a we've just found to be 3.27 times t, and that gives me a time of 4.28 seconds. Okay, so we basically had 5 marks for getting out our energy there, and 5 for getting 14. And we had 5 for getting our acceleration and 5 for getting our time. So the third part of the question then says, the disk is now replaced by a hoop of mass m and or. Okay, so we have to be careful with this. Okay, so the hoop has its own equation. So what I'm going to do is I'm going to draw a new diagram. And then we can see what page in our maths tables we need to look at. Okay, so again, it's not going to slide. So as it rolls, it'll again have angular velocity as it slides down, and it's going to travel exactly the same distance. So it's again going to have 30 meters down, which means the height is still going to be the same, where we said that was 15 meters. Okay, so the change in height is 15 meters as it rolls down a distance of 30 meters down the inclined plane. And again, there's no sliding. So the only difference being here is that it's a hoop. Now, obviously, for the purpose of this diagram, you have to distinguish that the disc is like as if you're cutting out a sheet of paper and it's a flat 2D circle, whereas your hoop is this infinitesimally thin hoop, a bit like a hula hoop, but obviously it's extremely thin. So our moment of inertia is going to be different for the hoop, and again can still be found on page 53 of your tables. And the hoop, the moment of inertia is m/r squared. So page 53. So again, the process is going to be exactly the same. So we want to basically get the acceleration and compare their ratios. So again, if we're looking at our principle of conservation of energy, it's again going to be our change in potential energy will equal our change in kinetic energy. So the loss in potential energy will equal the gain in kinetic energy. So again, we're going to have mass times gravity times height is equal to a half mv squared plus a half, and again moment of inertia this time is now m/r squared. Omega we saw was v squared over r squared in the previous part. Again, I can divide across by m, and my r squareds are going to divide into each other. And that is me with 15g equals a half v squared, this time plus another half v squared. And therefore that gives me 15g is equal to v squared. And v then is equal to the square root of 15g, and v is equal to 12.12 meters per second. So again, if I sub in to get my acceleration so that I can compare the two accelerations, well, final velocity we said there was, if we want to actually just sub in the third, keep it simpler and more accurate, and again we have 0 plus 2 times a, and again s is 15. So again, rearranging there to get a in its own gives us 2.45. Oh, sorry. And therefore comparing the ratios, so we say the acceleration of the hoop over the acceleration of the disc is 2.45 divided by 3.27, and basically that is our ratio of 3:4, which is what they wanted us to show. And there was 10 marks going for that. So again, 5 for working out our linear velocity and 5 for getting out our 3/4. So 30 marks in total then. Okay.